All right, class, we are on the second to last lecture for this unit, communities, succession, and biomes. So let's jump right in. So reviewing from a couple lessons ago, remember that a community is just all the different species and populations of those species interacting in one specific area. So it's all of the abiotic factors in an area. One thing that a community ecologist will focus on is something called ecological succession, and that's going to be the main focus of our lesson today. What it is just a series of predictable changes that occurs in a community over time. And this happens because new species are moving in and out of the area. What they hope to answer by studying succession is, how do communities change over time? So on the next slide, we're going to start by looking at a case study. What is ecological succession all about? What does it look like in real life? So we're going back to 1980 and the eruption of Mount St. Helens in Washington State, and we're looking at how succession has changed that landscape in the past 30, 40 years.
Mount St. Helens in Washington State is one of the most well-monitored volcanoes on the planet, and with good reason. It is still active, and more than 3 decades to the day after it launched a stunning and destructive display of lava and ash, it continues to transform a region and its ecology. Even now, scientists are still learning about the aftermath and how some life is emerging from the ashes. Science correspondent Miles O'Brien has the story, part of our new weekly series about exploring the leading edge of science.
36 years after its spectacular, deadly eruption, Mount St. Helens still rumbles and bears scars from that earth-shattering day. But hike down the slopes, away from the jagged crater just a little, and you'll see Mother Nature hard at work. And there's a good chance you'll bump into a team of scientists led by John Bishop. He is an evolutionary biologist at Washington State University, Vancouver.
The goal of our research is to understand how plant and animal communities reform after a catastrophic disturbance.
Bishop is one of a select group of researchers studying this rebound from a volcanic eruption. Back in 1980, Mount St. Helens had given scientists all kinds of clues that a big disturbance was brewing. 2 months before it blew, the volcano was venting huge amounts of steam, and there was a series of earthquakes. Even with all those ominous signs, the eruption was larger than anyone predicted. It happened at 8:32 on the morning of May 18, 1980. An earthquake caused the north face of the mountain to collapse.
After that, it uncorked an explosion that was directed horizontally and leveled the forest to 13 miles out from the volcano.
The eruption column of volcanic ash and gas rose 80,000 feet, while a tsunami of 1,800-degree gas and rock raced down the valley at 450 miles an hour, a so-called pyroclastic flow.
Anything biological that was remaining after the landslide would have been completely vaporized. It was just a barren landscape, gray and pumice-colored.
It killed every living thing in a 230-square-mile area. What was left was akin to a moonscape. 57 people died. Some remains were never recovered. Bishop and his team have had a front-row seat as nature got busy bringing this place back to life. They wanted to know where it begins and how it takes root. Here, it started with these purple flowers. Alpine lupin were the first plants to return. For many years, they were pretty much the only game in town. But as they went through their life cycles over several seasons, they created soil from the volcanic ash. And that made it possible for woody plants, like the Sitka willow, to find a home. They are how a forest gets started, but it hasn't been easy for them.
One of the things we've realized about these willows is that they're not getting big. That's important because they create habitat for birds and mammals. We've learned that these landscapes are characterized by extreme instability in the populations of the plants and animals that colonize them.
In a recovering ecosystem like this one, where just a few species have managed to regain a toehold, Even seemingly insignificant pests can play an outsized role in how the landscape bounces back. These weevils are an invasive species with a particular taste for the Sitka willow.
Any stem larger than about 1 centimeter is usually destroyed by this weevil. And the effect of it is to keep these plants small, not let them form the architecture that's needed for bird and mammal habitat.
But Bishop says it's important to remember we're still early on in what will be a very long game. He says the plants and insects will battle it out over time, and eventually the ecosystem will become more diverse, more stable, and this will be a forest again.
When I'm out there working on the pumice plain, one moment I'll look around and I'll be stunned by the amount of vegetation and the number of birds that are present. But then the next moment I step back and I think, there is hardly anything here. We're centuries away from replacing the old growth forest that was there.
Mount St. Helens is the perfect place to test an important question in ecology. Life does go on, but how? John Bishop will keep looking for the answer here, unless Mount St. Helens awakens and reboots the landscape once again. Miles O'Brien, the PBS NewsHour.
Mount St.
All right, so I thought that was pretty interesting, seeing how the new species are interacting with each other and how they're changing the landscape after that volcanic eruption. So that is exactly what succession is. It's how the community is changing over time, and it usually begins after a large disturbance like a volcanic eruption or a fire or deforestation. And like they said in the video, it takes hundreds of years for the landscape to go back to the way it was before the disaster. This is not something that happens very quickly. So there's two types that we're going to focus on: primary and secondary succession. So let's jump right into those. Primary succession begins in an area where there's no living community that has existed there before. So think primary means first. So this is the first community to ever be in this place. It usually starts from a situation of bare rock. And as you guys probably know, not a lot can grow on bare rock. So there's a lot of special circumstances that has to happen before we can get a nice growth of community here. So how do these situations start? These ones start from either a volcanic eruption or explosion, as you can see on the picture on the left here. This is after a volcano. This is all the volcanic lava that's hardened and left behind just tons of rock. It's how new islands form. So if you think about, islands start as just bare rock. So that's kind of how Hawaii started, and all these other places that we see is these beautiful lush gardens. So they had to start from bare rock, and all the species had to come years and years after that. Another way is from a glacier retreating. So if you can see in this picture on the right, there is the glacier, and as it's retreating or going back, it's leaving all this bare rock in its wake. Ice can be a really powerful force, same with liquid water. And as this ice of the glacier is moving back, it's tearing apart rocks, and it's scraping the landscape and leaving behind a place where nothing is growing. There's no living stuff behind it. So it has to start from bare rock. And eventually, depending on where you are, you'll get a nice different community that establishes itself at the end. So this is a community, or this is a succession where a whole new community must be formed from scratch. Now, the first species to arrive are called pioneer species. Think about the American Midwest and the pioneers that first went there. They were the ones that had to be really tough and really hardy, and they faced very horrible conditions. But by them going out west, they learned how to live in the landscape, and they made it easier for other people to move in down the road. That's exactly what's happening with our pioneer species here. They are the first to colonize the new area, and all they have is bare rock to work with. And rock does not really give them a lot of nutrients. So you have to have very specific species that can come in and transform the rock into healthy, nutritious soil. One of the main ones is lichen. Lichen is a symbiotic relationship between an algae and a fungus. So what this will do is actually break down the rock and turn it into soil. It makes the rocks very brittle. They fix nitrogen as well. So all the nitrogen that's in the air, they are converting it into nitrogen that's going to be in this new soil that they're making. Because remember, all plants need nitrogen to survive, and if they don't have it in the soil, they can't get it from anywhere else. That was part of the nitrogen cycle that we learned. They have to get their nitrogen from the soil, not from the air. Another pioneer species are moss. Another is grass. That's going to be a big one in our secondary succession. And you can always have a mix of all of these working. So we start with bare rock, and then we start getting all of these lichens and mosses and grasses in the area, and they're going to start transforming the landscape into soil. So let's watch this quick video that discusses what's going on in primary succession.
Ecosystems are shaped by biotic and abiotic factors. But before biotic factors like plants, animals, and fungi can become established, we need abiotic factors like sunlight, rainfall, and nutrients. And today, I'm here with ecologist Joe Mascaro, and he studies how ecosystems change over time. And Joe's going to help us understand how we can start with solid rock, and through biotic and abiotic factors, they can change this rock to support life. So let's track the stages of primary succession by visiting lava flows of different ages.
So, Suze, this is the earliest stage of succession, where the rock's been colonized by lichen and some small sword ferns. These guys will colonize lava right away, almost the day after it cools. And once they do, they'll begin the soil formation process. So they'll grow, and they'll start to break apart the edges of these rocks, which are really friable and easy to break. And then the lichen will fix nitrogen from the atmosphere, and that will begin to build up soil on the surface of the rock.
Now let's move to the next stage of succession, one that's a bit older.
Well, Suze, this flow looks like the ecosystem has developed a bit more than the last flow. So you can see how there's so much more lichen than there was on the previous flow. It's almost like a carpet. And as the lichen grows, it's basically breaking up the surface of the rock and starting the soil formation process, which is really happening in earnest now compared to the previous flow.
The first plants that become established are early colonizers. Early colonizers have other characteristics. They're fast-growing, they need lots of light, and they're usually wind dispersed.
That's right. And there's basically two types of early colonizers we might see on a flow like this. There's some that have a symbiotic relationship with fungi, and so they're able to fix atmospheric nitrogen directly and use it immediately. And then there are plants that are just able to tolerate really low levels of nitrogen, like ohia.
Okay, off to the next stage. So here we have an even older flow.
So we're actually going to see quite a bit more soil here than we saw in earlier flows. And we've really got a lot of moss. So we're really starting to see the ohias come together, and we're getting much closer to a closed forest. We're not quite there yet, but you can see how much taller they are and thicker.
Off to the next flow. So this is what scientists would call mature forest. It's over 300 years old. It might be hard to imagine, but this whole area was once barren lava rock. Let's go check it out.
So we're definitely in a later successional forest now, which means we're dealing mostly with tree species that are not wind dispersed. They typically have big fruits, maybe dispersed by animals. They're much slower growing, and of course they tolerate shade, And as a result of all those features, they tend to need a lot more nutrients over time to grow.
All right, so there you could see really clearly all the different stages of that primary succession there. And you could see how over time, more and more species can come into the area because more soil is being formed. So on to secondary succession now. This is going to occur in an area where there used to be a thriving community, but some disturbance caused it to be wiped out. Now from this point, we're not starting with bare rock anymore. There's still going to be soil in these places. So there's going to be a lot of nutrients, and it's going to be really easy for new species to move back in. So as a result, because they have all these nutrients available and they have soil, it's going to occur faster than primary succession. Breaking down that rock into soil takes a really long time. So primary is going to be the one that happens the slowest. Secondary is going to happen much quicker, but it still happens over a couple hundred years. Now, the pioneer species mostly with our secondary succession are your grasses and your insects. Now, there's certain cases where these natural disasters are actually necessary for the community to stay healthy. Some species of trees and plants actually need fires in order to germinate. Some species have a niche that only exists in a landscape that's been destroyed by a disaster. A healthy landscape doesn't support them, so they have to move from an area that's been destroyed to a new area that's been destroyed because that's where their role in the ecosystem is. So here's some examples of secondary succession. If you look, there's no point where we have just rock. There's always going to be soil here. So you start with your weeds and your grasses after some type of big disaster like a fire. And then you'll get bigger and stronger and more rooted species as we go on. And this is more than just plants. We're also talking about animals as well. They just often don't show them in these pictures, but the first species that you'll get back are usually insects or small rodents after the insects, or birds that will eat on they'll eat all the insects. Okay. Now humans are a main cause of secondary succession occurring nowadays. Of course, there's a lot of natural events that cause this, but we're a big cause in modern times. We might cause deforestation in an area that we want to build in, or that we want to use those trees as raw materials. We often will destroy a landscape so we can put farmland there. We'll let cities go to waste after a while. So some areas, if the city doesn't do well, we'll abandon it. And that is a succession situation as well, where all these things have to start building up from scratch. Now, even sometimes we cause forest fires. It might be to keep the landscape healthy, and it may be by accident. Maybe there's an accidental fire that starts that destroys the landscape. Now, there's been some evidence recently that shows when humans are the cause of the disaster, we often end up destroying the landscape in a way that makes succession harder. So if a natural disaster occurs, there's usually still a lot of nutrients left behind. But if we have deforested, if we've farmed the area very heavily, the soil is often very depleted of nutrients. So it'll take a lot longer to build those nutrients back up before all of the species are able to start coming back and establishing a presence.
There is a rare and magical kind of forest in the American West. This forest is ephemeral, springing suddenly into being. We never know where it will appear next. It is the home to a unique community of plants and animals. This fleeting forest is as ecologically valuable as our treasured old-growth forests, and even more scarce because it's so short-lived. In momentary magic, it flowers and thrives for just a handful of years, providing home to a ride of life. Countless creatures come from miles away to partake of its seemingly endless bounty. This is the intensely burned forest. It begins with a lightning strike deep in the forest. A tree ignites and a fire soon spreads in a natural event that has been repeated innumerable times for millennia. Native beetles sense the smoke and heat from miles away and immediately swarm in huge numbers to the newly burned forest. These beetles deposit millions of their eggs inside the dead and dying trees. The beetle eggs soon hatch into larvae, which feed upon the sapwood under the blackened bark. Rare black-backed woodpeckers also sense the fire and flock to the burned trees to feast upon the superabundance of beetle larvae buried within. Woodpeckers are designed especially for drilling holes into freshly dead trees and extracting larvae with their long, sticky tongues. They use their specialized heads and bodies to excavate safe, protected cavities in the dead trees where they raise their chicks. When woodpeckers are finished using their cavities, other birds that cannot make their own nest in these abandoned holes. The seeds of specialized shrubs and flowers, which have been waiting for fire to open them, begin to grow in the soil enriched by the burn. These blooming annuals and perennial shrubs attract legions of insects which feed large numbers of bug-eating birds. Some birds, like mountain bluebirds, house wrens, lazuli buntings, and black-backed woodpeckers, are hardly ever seen in unburned forest. Mammals, too, thrive in these intensely burned forests. Mule deer congregate to devour fresh vegetation made more nutritious by fire. Small mammals, like deer mice and voles, increase dramatically after a fire, eating exposed seeds and new vegetation and finding shelter under fallen logs. Naturally, the abundance and variety of small mammals and songbirds attract forest predators seeking a meal. But this magical forest is short-lived. As soon as the fire has cooled, the forest that was there before begins to grow again. Beetle droppings and bat feces accumulate at the bases of burned trees and nourish the soil, thus helping the next generation of trees to grow. As the dead trees begin to fall, the wood decays and further fertilizes the forest floor. Just a few years after the fire, the green forest is already returning. The creatures that depend upon the freshly burned forest must move on, waiting for the next lightning strike to create their magical and fleeting habitat.
So you can see how everything is so interconnected when we're talking about these communities in succession. One species affects tons of other species. One small incidence of creating that hole in the tree by the woodpeckers creates a home for so many new species of animals. So all of this is very interconnected. There's no way that one species can move into an area or leave an area without affecting the ecosystem behind it. Now, at the end of succession, what you end up with is something called a climax community. So this is the community that is stable. It's no longer dealing with a lot of species moving in and out like it was early in the succession stages. This is a balanced ecosystem that's thriving. Many different communities of organisms have moved in. Now, the climax community before the disturbance is almost always the same one that you'll see after the disturbance as well. Especially when we're talking about secondary succession here. That's because all of the abiotic factors are very similar still. You're still dealing with the same type of climate, the same soil type, so you'll get the same species moving back in. It all depends on the environment itself. Now, in your notes, I want you to answer this question. What does a normal community even look like? At what point can we say that this is normal? Is there such a thing? So write down what you think the answer is and why you think it is, and then when you're ready, move on to the next slide. There's two other types of succession that I want to talk about. The first one is ponds, so a freshwater ecosystem. So sometimes you'll get these areas of land that fill up with fresh water. And they begin as an empty freshwater pool with no other living things in there. That's because the soil isn't exactly fertile and there's not a lot of sunlight getting down to the bottom. Over time, that pool is going to start filling with sediments that are getting blown around or moved around by animals and plants. And that is going to create a nice layer of fertile soil. It's also going to make the pond a little more shallow, so species can move in and put roots down. Over time, more sediments get trapped. A marsh community will form, one that's kind of half wetland, half normal soil. And then eventually it's going to fill up, dry up, and trees are going to spring up in that area. So after the pond fills up with soil and all the water dries up, what type of succession do you think is occurring? Is it primary or secondary, and why? Pause the video, write down what you think it is, and then move on. The other type of succession that we're going to focus on here is aquatic succession. So we've been focusing on rock and soil and all the land communities, but we have to remember that 75% of our Earth is covered in water, and there's thriving ecosystems and communities there as well. So how do they handle succession? So you may have a hurricane that wipes out all of the life in a coral reef. You may have a shipwreck, and that ship will then float to the bottom of the ocean, or sink to the bottom of the ocean, I guess I should say, and create a new area where plants can grow and animals can live. A really interesting one is this one in the blue picture here. When you have a very large animal like a whale die and sink down to the bottom of the ocean, it is actually going to create a small little ecosystem or community down there of all the animals that are going to come and feed on it. And this will actually last for quite a long time, quite a few months, and you'll have these stages of different animals moving in, and you can read them all right here. Another place where we see aquatic succession a lot is coral reefs. So coral reefs will often form where there's a lot of lava flow, or they're the ones that often get hit the hardest when you have a natural disaster. So the coral life will be destroyed, and then it'll have a chance to come back over time. So that was a video that's discussing actual research going on from scientists just down the road from our school at CSUN. So you can see that the effects of the hurricanes damaged a lot of the coral reefs, and they are trying to find out now, how does the coral reef bounce back from that? So we've looked at how succession happens, but why does it happen? I've kind of hinted at this a couple times, but let's say it directly now. Every organism will impact its environment in some way, big or small. So you may be the little species that comes in, but you're food for another species. So your impact goes far beyond just your presence there. You're going to be fueling your environment in some way or another. So as these organisms move in and out of an area that's changing because of succession, they are going to be changing their environment just from their presence or absence. Now, the last thing we're going to talk about very briefly today, because we're going to spend the whole next class talking about it, are biomes. Remember that this is the level above ecosystem. It's mostly determined by the regional climate. So these are many ecosystems with the same abiotic and biotic factors. So we're looking at a much bigger area than just one ecosystem. So things like climate, rainfall, temperature, these are all going to play a really big part in how we determine our biomes. So some examples that you guys have mentioned in class, things like tundra, tropical rainforest, the savanna, the temperate grasslands. So let's look at a couple of these just very briefly, because I want you guys to actually study these on your own, and we're going to do a little project with them. So the main biomes of the world can be seen on this map here. And I want you to take a moment and maybe pause the video, and I want you to answer this question for me. What trends do you see? How do the biomes change based on where you are in the world? All right, pause the video, write that down, and then we'll move on. So as you can see, you tend to have very similar biomes at the same latitudes. So if I'm looking at the equator, which is this line here, I see a lot of this green biome surrounding it. That's going to be my tropical rainforest, and that's because around the equator we get very stable amounts of sunlight, we get a lot of rain, and we get nice warm temperatures. Now up here, we get this taiga, where we have a lot less biodiversity, a lot fewer organisms there. It's much colder. It has a very different type of rainfall than we do at the equator. So latitude directly affects the climate, which is going to directly affect what type of biome you have. So you have this desert biome. This one's characterized by very low precipitation, very low rainfall, and very high temperatures, especially in the summer months. The savanna biome, this is the one that you often hear talk about in Africa, the one with your zebras and your lions. This one has very up and down rainfall. So you'll have a very rainy period, followed by some minor rains, and the temperature remains very stable throughout the year. In the tundra biome, we have very, very little rainfall, almost as little as the desert, and very low temperatures to match that. So the desert has high temperatures, the tundra has very low temperatures. In the temperate forest, this is going to be like the east coast of the United States, you're going to have very stable rainfall that's not quite as low as the desert and the tundra, but not quite as high as you have in a tropical rainforest. And your temperatures are going to fluctuate with the seasons, so colder in the winter, warmer in the summer. In the tropical dry forest, you're going to have a lot more rain differences based on the season than you do in the regular forest that we just showed you. And the temperatures are going to stay a lot more stable. Now, this is our biome here in Southern California, the chaparral biome. You also might hear it called the temperate woodland and shrubland. It's also the same biome that you'll get in the Mediterranean. It's categorized by very little rainfall, but a little more seasonal rainfall than in the desert. So in the winter months, you'll get a little bit more rain than you do in the desert. And the temperatures stay pretty stable, but pretty high throughout the year. Then you have your coniferous forest biome. So these are our conifers. And you'll have rainfall and temperature that varies and fluctuates with the seasons. And finally, we have here our tropical rainforest biome, categorized by very stable temperatures, very high rains. All right, so I want you to answer this question. Which two biomes do you think have the most species of plants and animals? And which two biomes do you think have the least amount of species, plants and animals? So explain your reasoning for that too. Don't just put the biome names. Explain why you picked those ones. So pause the video, answer that, and then move on. All right, guys, we made it to the end. I know this was a long one, but I thought those videos really showed how succession happens in real ecosystems for you. So what we covered, we talked about what communities are. They're the level of organization that focuses on the populations of different species interacting in the same area. Part of community ecology is the study of ecological succession, which is how communities will change over time as the species move in and out. You have primary succession that occurs where there was no community there before. They must form a new ecosystem from bare rock. And then there's secondary succession where you had a community and it was wiped out by some kind of disaster, but we still have soil to start out from. Now, succession can even occur in aquatic communities as well. Remember, we talked about the pond and the ocean with the whale and the coral reefs. Succession occurs because species will always change their environments by their mere presence. And finally, we discussed biomes, groups of similar ecosystems that are characterized by their climate. If you guys have any questions or you didn't understand a part of this lecture, please write them down and bring them to class so we can discuss them next time I see you. Have a great weekend.